So my name is Val. I'm with GridGain Systems. I'm a solutions architect there. And I'm also one of the committers of the Apache Ignite project as well, one of the regional committers. So I'm with GridGain for like several years already, and during my employment with GridGain, I did a lot of different kind of stuff. I started as a developer, like doing deeply technical stuff. Now I'm more like working with customers, with our customers and users, like helping with their technical challenges and with building their applications that are based on Apache Ignite mostly. So by no means I'm the biggest expert in distributed systems, but I like to think that I have certain experience in that area, in Apache Ignite in particular, in distributed systems in general, and in building like actual applications based on these kind of systems. So today I would like to share some of that experience. And I want to talk about several different pitfalls that can evade you when you're working with distributed systems and when you're building applications based on distributed systems. And of course, I will talk about the ways to avoid those pitfalls and work around them. So just basically starting with some basics about what distributed system is. So here we have like a typical diagram, architectural diagram of a distributed system that stores data. Right? And we have several nodes here, which are actually used to store the data, right? And the data is distributed across those nodes or partitioned across those nodes, which means that every node actually holds the small portion of the data set, right? That allows us to easily scale out. So we can add more nodes into the system when we run out of resources, when we don't have enough memory for all the data, or we don't have enough computational resources to do the processing, to execute queries, or whatnot. And then on top of that, we have different APIs, right? So we can have like key value APIs, which is typical for data grids. They usually provide key value APIs and some compute capabilities. We can have SQL APIs, which is typical for like distributed databases, which are more SQL-oriented and provide comprehensive SQL support. Apache Ignite has both key value, compute. It also has the SQL support, transactional support, streaming support, some others. And by the way, this diagram is from Apache Ignite as well. So, and all my diagrams and all my examples, like code examples, particular terms and particular APIs that I'm going to show are from Apache Ignite. But like, general concepts that I'm talking about, they're applicable to many different distributed systems. And if you're guys using something else, not Apache Ignite or GridGain, you would probably still find some useful information there. All right, so what is the challenge with the distributed system, right? So what is the biggest challenge there? And the biggest challenge with the distributed system is the fact that it's distributed. Simple as that. And just to explain this idea a little bit, I have this kind of analogy that I like to use for that. So we have two cavemen here, right? And they both want to, for whatever reason, bring like a big piece of stone to their caves. The guy on the left happens to find like a very huge boulder which just lies on the ground, and he tries to push that boulder. I mean, obviously barely succeeds because it's very heavy and it's hard to move it. But there is a second guy who is more lucky, and he found this kind of a circle-shaped kind of stone, so he can roll it and proceed much faster. So, I mean, those two guys, they probably don't really understand what's going on here and why there is so much difference in these like two approaches to the same problem, basically, right? But we all here know that the reason for that is the friction between the boulder and the earth, right? So in the first case, the amount of friction is huge, so it's very hard to move the stone. In the second case, the amount of there is much less friction, so it's much easier. So it kind of looks like there is a very simple, straightforward formula to that, right? So we minimize the amount of friction and we're good. But it turns out it's not quite true. Because in this case, there is still some friction, and it actually moves because there is friction. And if we minimize it to 0, it will just roll but not move. So it turns out it's actually a matter of not minimizing the friction, but having a certain amount of friction so that it's enough to move the stone, but not too much so that it's hard to move it. And it's also a matter of like properly applying it in the right direction and all that. And in distributed system, we have the exact same story. And in distributed system, our friction is network communication, one of the main frictions at least. Because network is essential for any distributed system, right? There is no distributed system without network. It's basically one of the ways to communicate between nodes and to coordinate between nodes. So network is used for this coordination. And basically, on top of the advantages that distributed system provide, we also get this overhead, which is created by the network communication and by this coordination between nodes. And if your applications that you build on top of distributed system, like your API invocations that you use there, or your SQL queries that you execute, for example, they trigger too much network communication, performance just goes down. And instead of getting the advantage from a distributed system, the performance gets even worse. So how do you avoid this? How do you avoid those bad situations? So in my view, the main thing you need to understand to avoid this is to basically understand how data is actually distributed across the nodes, across the nodes in the cluster. Right, so I will use, obviously, again, I will use Apache Ignite as an example. So let's answer this question. So we have a cluster of 2 nodes, for example, right? There's node 1 and node 2. And we want to save something in that cluster. So we're using key value APIs, and we want to put some key value pair into that cache. So on the client side, you would just do the API invocation. You would just call the put method. But where would it be stored? So that's the question we want to answer here. So obviously, I mean, different systems do that in different way. I mean, every distributed system would have its own way to do that. Apache Ignite does it in the following way. So in Apache Ignite, we have multiple partitions, first of all, like constant number of partitions, like 1,000, for example, in the cluster, right? And every partition is like, you can think of it as a bucket for your entries. It's like a hash function, basically. When you map a key to a certain partition, it's just basic hash function. So we take the hash code of the key, of the primary key, apply the modulus function using the number of partitions, and select the bucket this way, select the partition this way, like similar to what you see in like a hash map. So for example, we have a partition 1 for like 4 entries, and then we have some other partition with some other entries which are not related to those 4, right? And then we need to distribute those partitions across the nodes. Again, there are many different algorithms possible here. Like in a very naive approach, you can just do, like a round robin thing where you have 0 node 1, partition 1 on node 2, and so on, right? This algorithm would never actually be used in a real system, but that's a possibility too. So that actually brings us to this kind of 2-step mapping here, right? So whenever we want to decide on which node we store a particular key, we would go through this 2-step mapping. We will first map our key to a partition number, and then map our partition number to the particular node. What's important to understand here is that the first step is constant, because the hash code of the key is obviously never changes. The number of partitions also never changes. It's a constant number, like 1,000 or 2,000, for example. And it's a very simple step. But the second step is much more complicated, and it's dynamic, because this one, we need to recalculate every time topology changes, every time we add a node into the topology or we remove a node from a topology. And that's actually the reason why we have a 2-step process, why we do not map keys directly to the nodes, because in this case, we would, every time topology changes, we would have to recalculate the mapping for every key we have, which can be like a very huge number. So in Apache Ignite, this is actually encapsulated in what we call affinity function, which is basically kind of a component which is available on every node. And every node at any moment of time can consult this function, can invoke this function, providing the key and the current topology state, and get the node where this key is stored. So going back to our question that we were going to ask, that's exactly what we would do in this case. We would invoke the affinity function, And affinity function will tell us where this key is stored. So for example, if it, if it tells us that our key is on partition 2, which is on node 1, we will send the request on that node 1. We would never go to the node 2. Which is basically like, the main recipe for scalability and performance, because we don't have to do any additional hops. We don't need to try first node and then second node, nothing like that. We just go directly to the node where we have this entry. All right. Now, how can we use this information, this knowledge about data locality, to actually improve performance and scalability of our applications? So, of course, there are many approaches to that and many ways to do that, but what I'm going to talk about is collocation. Collocation is kind of an umbrella term for different kind of things, but what they all in general mean is that basically you know where a particular entry is, right? And you put something else next to that entry, directly on that server node where this entry is stored, so that the actual entry is not moved around. And one of the most obvious examples of that is collocated processing. So collocated processing is basically the approach where instead of moving data around, instead of moving the data to some processing node where processing happens, you move your computations like closures or lambdas to the nodes where the data is stored. So this is shown on the right picture here. So when we want, and you can think of it as an alternative to client-server processing or traditional client-server processing, where we would fetch the data from server nodes, like fetch some certain subsets of data from all the server nodes, for example, collect them all here on this processing node, do the processing here, and then probably update something back if you need that. So with collocated processing, you instead send the closures like lightweight requests to those server nodes, do the processing there, get partial results, and then do the final reduce step on the client node. So again, remember, we're trying to reduce the amount of network communication created by our applications, right? So that's one of the ways to do that, obviously, right? So we do not move all this data around, which reduces the communication a lot. And in many cases, this gives a lot of improvement. Like a simple example here. Very typical, use case of updating an account balance, right? So we have an account object with some metadata about the account, like owner's first name, last name, address, social security number, and whatnot. And then we have the actual balance number, which represents the current balance for that account. And then we want to update the account by subtracting $100, for example. So, the account's owner swiped the card somewhere, buys something for $100, and we want to update the balance. So how would we do that with the traditional client-server approach I was describing before? We would do this. We would read the data first. So we would do a get operation, providing the account ID, get the account object, update the balance in that object, and then put it back. So from functional standpoint, all is good here. That this code is going to work. It will update it will probably properly update the balance. It will do what we want. It will be atomic and consistent, assuming if you wrap it in transaction and everything. So nothing is wrong with this code from functional standpoint. But from performance standpoint, this one has at least two problems. Problem number one, we have to do the round trip to the server node twice. First one when we read the account object, and the second time when we write the account object back. And problem number two here is that every time we do this round trip, we fetch the whole account object, which can be pretty big. It has all the metadata, it has all the information about this account, which we don't really need. And if you think about this, it's not really what we are looking for. It's not really what we want to do. Why do we need all this information about this account on the client node? Why do we even want to know what is the current balance of this account. What we really want to do, we want to tell our database to update an account with a certain ID by subtracting $100, and then just get a confirmation that everything was fine, right? So obviously, there are different ways, many ways to do that. It's a very simple example, but one of the ways to do that is this API, which is provided by JCache. So any distributed cache or any data grid that implements JCache would have this API. This is entry processor interface and invoke method, which are like used in conjunction. And it does exactly what I just described. So entry processor implements the actual logic, the actual processing logic that you want to do with that account, and it will be executed on the server node. So this way, we solve both problems. First of all, we do a single cache operation, so we don't have to go back and forth twice. We do a single round trip to the server node and back, and we don't transfer the account object across the network. All this code here, which is inside the entry processor, happens on the server node, where this entry is stored. So this read that happens here is local to that node. The account object is never transferred across the network here. So again, I mean, from functional standpoint, this code does exactly the same. There is no difference. It updates the account balance and subtracts $100 from that balance. But from performance standpoint and from scalability performance, the difference is huge. Like the latency of this operation would be probably orders of magnitude faster than the latency of the previous example. Okay, so previous example showed how you would do this kind of collocated processing with a single entry in the cache, right, or in your data grid. But what if you want to collocate an entry with some other entry, or to collocate several entries together, basically like creating a group of entries which are logically connected to each other, although they're separately stored in cache. Another example. So this is like a payment transaction authorization example. This is like a use case from banking area. So what we do here is we want to authorize the transaction every time someone swipes the card. So every time someone swipes the card, we want to create this transaction object, which is very simple. It has the account ID. It has the store name, like the name of the store where it happened, like Walmart or Target or whatever, and then the amount of the transaction, right? But before actually applying this transaction, we want to authorize it. And to authorize it, we want to go through all the, or maybe not all, but the latest history of transactions for that account, calculate certain like authorization variables, and then make the decision based on that. And we want to do this in real time. And we do not want to actually save this transaction in a cache if it's not authorized. So how do we do that, right? By default, all our transactions are randomly distributed across the nodes. We didn't do anything yet, right? So different transactions for the same account can end up on different nodes. So how can we go through all of them? Yes, we can use our client-server approach. We can fetch all those transactions for the same account ID to some other processing node, do the authorization there, and then save it back as needed, if needed. But that's not really performant, because we have to do a lot of back and forth. We have to transfer a lot of data. This processing node has to be very powerful, so there are many problems with that. And what we want to do to solve this problem is we want to make sure that all these transactions for the same account are on the same node. So we create this kind of a logical group of those transactions that we want to store on the same node. And so that, and we also want to do to have an option to do the processing there, right? So we want to achieve two things here, right? So first thing is we want to make sure that all the transactions for the same node, for the same account, are on the same node. And we want to have an ability to send a computation to that node based on the account ID, right? So that's how this is done in Ignite. Coming back to that mapping that we had before. So we have a two-step mapping, right? So we map a key to partition and then to a node. So what we did in Apache Ignite is actually, it's kind of an elegant solution, I think. What we did is we just added an additional step here. Before all that happens, we map the actual cache key, which is kind of a primary key, right? It's unique for every transaction. It's unique for every entry, for every record in our database or in our cache. So this primary key is first mapped to what we call affinity key. So affinity key is basically what we use for affinity mapping, for mapping to partition and then to a node. And affinity key doesn't have a requirement to be unique for every transaction. It can be the same. So I mean, pretty natural we would use the account ID here. So if we somehow make sure that all our different keys, different transaction IDs for the same account are mapped to the same account ID, which seems to be pretty simple, they will end up on the same node. The actual algorithm doesn't really change here. The mapping itself happens in the exact same way. And then obviously knowing the account ID, we can also send a computation, right? When we want to do the computation on that node where the data for this account is stored, we would again invoke our affinity function, provide the account ID, and it will give us the node. So that's how it looks in code. So basically what we need to do here is we need to create like a transaction key class, right, with two fields. So the first field would be an actual transaction ID, which is our like unique identifier of every transaction. And then we have the account ID here as well. And the account ID field is mapped by the special affinity key mapped annotation, which instructs Ignite to use this field as affinity key. So every time you save something or do any operation, providing an instance of this transaction key class, the mapping is going to happen not based on transaction ID, but based on the account ID. So obviously, all transactions that have the same account ID would end up on the same node. And that's what we're looking for. And we can also do the computation like shown here. There are special APIs for that, like affinity run method, for example, where you basically provide a cache name. You provide the affinity key, which is account ID in our case. And then you provide an actual computation, like a closure or a lambda. And this lambda will be sent to that server node where all the transactions for this account ID are, and would do all that processing. Like remember, we would iterate through the transaction history, calculate our variables, and do the authorization. So all the processing now is going to happen on that node where these transactions are stored. So we don't have to transfer a single transaction across the network. All we do is we send this lightweight request, this lambda, to that node. And then get a confirmation, or basically an answer, indicating if transaction was authorized or not. All right, so far my examples were involved like using key value APIs, right? But what if you're not using key value APIs? What if you're using SQL in your applications, right? There are many distributed databases that support SQL. Ignite also does. So would collocation affect you in this case? Actually, it would, and it can be even more tricky. And you probably should be even more careful with that. Because in this case, when you're doing this arbitrary search and you're not actually working with cache keys or affinity keys, it's much less obvious how collocation affects the execution of your queries. So let's go through a couple of examples here as well to demonstrate what can happen if you enable or disable collocation. So in the first example, we would analyze how this query is executed. So our data model is actually the same as in previous example. So we have our transaction object, which has like account ID, store name, and the amount. And what we want to do is we want to calculate the average amount for a certain account. And let's take a step back and assume we don't have any collocation yet. So just imagine we don't have this authorization process. We just save those transactions in the database once they come. And I will compare the execution of this query with one node and 3 nodes just to show you how the scalability works in this case. All right. So by default, unless you configure any indexes, there is no indexing, right? So every time you execute this query, you have to do a full scan, basically. Like if you have 3,000 transactions, for example, for all the accounts, not only for the account that we're interested in, but for all the accounts. We have to scan all those 3,000 transactions to find the transactions that correspond to our account ID and do the aggregation. So with single node, it's fairly straightforward. We would iterate through those 3,000 transactions on that single node. If we have 3 nodes, that scales out pretty well, because now every node has only 1,000 transactions, and we would iterate through 1,000 transactions on every node, and we would do that in parallel. So latency is 3 times less in this case. Capacity is 3 times more because we have some available resources that can be used for other queries that can be executed concurrently. Capacity here, by the way, is like a maximum possible throughput. So like maximum possible number of queries that you can execute concurrently in parallel without compromising the latency, so that basically queries do not wait for each other, right? All right, but in this particular example, with this query, you would probably have the index, right? You would create an index on the account ID field. If the system provides this capability, you would do that, of course. So what is the index, and what happens if we use the index? So sorted index is usually like a tree structure, like a sorted tree structure. So with a single node, you have this single tree structure, and when you execute the query, instead of scanning all the data, we would actually go through this tree. But what happens if we have many nodes? If you have many nodes, it's like a forest, right? So we have many tree structures. So it's not only the data is distributed, but the index is distributed as well in the same way. So every node would hold its own sorted tree structure that corresponds to the data that is stored on that node. And we would go through all those tree structures in parallel. But what happens to the latency in this case? So the algorithmic complexity of the index search is logarithm, as we all know. So like if we have 1 million entries, we have to do approximately 20 iterations through the sorted tree, in the worst case, of course. And if we scale out this to 3 nodes, that's what we get. So the amount of entries on every node is much less. But the amount of iterations that we need to do through a tree structure, through the index, is pretty much the same. You would not even notice the difference between those two. And that's the result that we get here. So basically, every node now has to do the exact same job as this single node that executed this query. So the latency is the same. Capacity is also the same for exact same reason. So basically, we just created a completely non-scalable system. And I just want to just think for a second about this. It doesn't look like we did something wrong, right? We created the data. We created a schema. We created a table in a database. We put some data into the table, and then we executed a query. But the performance is the same with 1 node, with 3 nodes, and with 1,000 nodes. It doesn't really change, and it does not improve. That's not what we expect from a distributed system, right? We want a distributed system to be scalable and provide better performance when we add more resources, when we add more nodes. So how do we solve this? And it turns out that collocation is also an answer here. So let's now investigate how it would work if we actually collocate by account ID. So we do the same thing as we did before. We collocate those transactions by account ID so that all the transactions for the same account are in the same node. And once we do that, the query engine, while it parses the query, it can actually detect that there is the account ID equals something criteria, and therefore it can invoke the affinity function, find out where the data for this account is, and send the query only to 1 node instead of broadcasting it across all the nodes. And once we do this, we get this kind of picture. So now, if we execute only 1 query, and we have 3 nodes, only 1 node is actually busy. Other nodes are free, and they're available for execution of other queries for other accounts And this can be done concurrently in parallel. And this effectively increases our capacity, increases our maximum throughput. Latency, of course, doesn't change because, I mean, regardless of how many nodes we have, we use only one node to execute a single query. So the latency of the particular single query doesn't change, doesn't depend on the number of nodes we have. But that is probably fine because we used indexed search here. So the latency of the query is most likely pretty good. If you have like good selectivity, if everything is optimized, I mean, if you have like a more complicated query and you optimized it properly, you have all the indexes and all the stuff, the latency is already good. So what you're looking for is you're looking for an ability to execute more queries in parallel and to handle higher load by scaling out the system. And that's what we are getting here. OK, and finally, least but not least, I want to talk about joins. I mean, when you work with SQL, you would most likely use joins in some of your queries. So let's take this data model as an example. So we have like a country table and we have a city table, right? And they have one-to-many relationship between them. So city table would have like a country ID field, which is a foreign key, and references the country table. Fairly straightforward, right? So if we do not do any collocation, we get some random distribution, for example, like shown here. So we would have some Canadian cities here, Toronto and Calgary, some Canadian cities there. The record for the Canada itself would be here. The same happens to India and to all other countries. And when we execute this query, the query that involves join, like shown here, for example, we would broadcast it to all the nodes. And if we do the local join on every node, we would not get all the results, right? Because here on the first node, the join would return us Toronto and Calgary for Canada, but we would lose Montreal and Ottawa. And the same happens to India. Like we would only find the New Delhi here, but we would lose the Mumbai. So to solve that, we would have to reshuffle the data somehow while we execute the query so that all these cities are joined with the corresponding countries. So this actually works, and this is called a non-collocated join, and it's supported by most of the databases, including Ignite. But performance of this kind of execution is not very good, obviously, because it involves a lot of network communication. It involves a lot of data movement. Systems support that because I mean you cannot always predict every possible join in the system, especially in like analytical use cases, for example, where you have ad hoc queries executed by your users, by the users of the system, and you physically cannot predict everything that's going to happen there. So in certain cases, you might want to allow this kind of a non-collocated join. If it doesn't happen too often, if it happens for queries that are not so important from performance standpoint, then it's OK. But for most of the queries, you want to collocate. And to collocate, we would, again, do the exact same thing as we did before, right? So what we want to do here is we want to make sure that all our cities that belong to the same country are collocated together. And they're also collocated with the actual row in the country table that represents the country they belong to, right? So for country, we don't need to do anything specific here because our primary key is actually the affinity key. So country ID is going to be our affinity key, obviously, right? So that's our criteria for collocation. So for country, we don't have to do anything specific. Our primary key, our cache key, is affinity key in this case. So we just save it as is. But for city, we would have to create a primary key that consists of two fields, which is city ID and country ID. And then we will instruct Ignite to use country ID as affinity key. So like, for example, the record for country with ID 5 would go to the first node. And then all the cities that have country ID equals 5 would also go to that first node. If there is another city which has another country, like country ID 9, for example, which is a different country, it could go to other node. So we are fine with that. But everything with country ID 5 has to be on the same node where the country 85 is. And once we do that, we get distribution like this. So like we would have a Canada here and all the Canadian cities right next to Canada. And the same happens to India and again all other countries. So now when we execute the exact same query, we can just broadcast it across all the nodes that we have and execute the join locally on every node. And all the data will be properly joined and properly found. We don't need to do reshuffling. We don't need to bring like Canadian cities that are absent on source node because we collocated them. Yeah, so basically, I mean, this is also one of my favorite examples. Actually, it's because again, I mean, in two latest examples with the non-collocated join and collocated join, everything was the same, right? We had the exact same data model, we had the exact same data set, we had probably like exact amount of resources and everything else, but and exact same query as well, of course. But the result would be very different, the performance result. The performance result of the collocated join would be, again, like orders of magnitude faster than the result of the non-collocated join. And this example, as all other examples, I think they kind of give an idea of how collocation affects the execution of your computations, of your SQL queries, and whatever you do on your distributed system. And shows why it's important to know and understand how it works under the hood to a certain extent, to understand how data is distributed across nodes, and how this distribution and collocation affects performance and scalability. That's actually all I have for you. And I think we have actually 12 minutes, so I'm ready to answer your questions. Go ahead. Mm-hmm. Mm-hmm. Yeah, so yeah, I mean, yes. So first of all, Ignite can have backup copies, right? So you can configure how many backups you want to have, right? So if you say I want to have one backup, that would actually mean that for every record, for every entry, you would have 2 copies in the cluster, right? So that would be primary copy somewhere and the backup copy somewhere else. And you also can have a fully replicated cache, which means that the data set is fully available on every node. And you can mix and match. So you can have caches or tables which are fully replicated and tables that are partitioned at the same time. And yeah, you're right. Like in this particular example, if we replicate the country table, we can achieve the same collocated, it's not collocated, but we can achieve the join without data reshuffle, without actual collocation. But in many cases, you cannot really do that. Replicated caches are usually used for like reference data, this kind of stuff. When the table is small, is not updated frequently, then yes, you can put it into replicated cache, and then you don't have to worry about the collocation of that table. But for any table that can grow in time, that requires scalability, it has to be partitioned. And that's where collocation helps you. Mm-hmm. Yes, you can. So basically, in this case, I mean, it would depend on how you actually configure that because there are different ways, right? So I showed like this annotation-based way. In this case, you can have like an object with those 3 fields that would be used as affinity key, and then you would encapsulate it in your. In SQL, yes, in SQL you can create your tables using DDL commands, and then you provide the affinity key field name. I'm actually not sure about. That's a good question. I'm not sure if you can do that with DDL command, like directly like that. I'm sure there is a way. There is I mean, we can brainstorm and find a workaround, but I don't think you can directly specify, like in this create table command, that you want to use multiple fields for affinity key. I'm not sure about that, but we can check it separately. But I mean, technically, like the product architecture doesn't limit you to a single field, so you can have like a composite object that is used for affinity key. So maybe there might be a limitation with DDL, which I'm sure has a workaround, but architecturally there is no limitation. So technically it's possible. Yeah.
My question is for analytics workload.
Mm-hmm.
I have a sale line, and my analyst, I don't know how they will analyze. They want to analyze by customer, by region, by product,
Yep.
by different kind of things. So how do you design that co-location when you replicate that?
I mean, as I said, right, so when I was talking about joins, I mean, especially in analytical use cases, you're right. It's not possible to predict everything, right? But most likely, I mean, in most systems, there are certain patterns. There are certain, join criteria that are more frequently used, and that's where you would collocate. If you do not collocate for like small amount of queries, that might be okay.
No, but in an analytical system, then most of the time it will not be co-located. So then the question is when the performance hits then not.
No, I agree. I mean, of course.
Analytical workload.
I mean, I agree. Of course, my examples are very simple. They do not represent any real system. And in a real system, it's a much more challenging task to find a proper collocation strategy. And it's actually case by case. So in general, you would have some caches partitioned, some caches replicated. You would choose certain collocation strategy because this join is more frequent than others. Sometimes you can, if performance is important for you, you can duplicate the data, right? So you can duplicate the table and collocate by different criteria, right? And then do the joins correspondingly. So there are different, tactics and different approaches how you can improve the performance. But analytical use cases are actually pretty challenging because of that. That's true.
And how do you take care of multi-table joins on the different keys? Multi-table join, but they are not joined on the same key.
Yes. So I mean, usually in this case, one of them should be or has to be replicated, or it's going to be non-collocated join. So like if we join with the country here, for example, and then we have like I don't know, we have a reference table with like zip codes, for example, right? Then these reference tables would be replicated. Mm-hmm.
Once the affinity key has been set and the cache is populated, so I'm guessing the data is going to the right node, right?
Mm-hmm.
Is there a way for me to I kind of figured out that's the wrong affinity key, and I want to switch to a different one? Do I have to recreate the cache, or
Yes.
is there a way for it to actually?
Yeah, you have. I mean, you will have to like move the data around anyway. So you basically just recreate the cache and reload the data, right? There is no technical way to do this dynamically without destroying the cache and recreating it. But even if there was, it would basically do the same because it would have to like move all the entries like to some other node, right? And it would have to reshuffle the data, which pretty much the same as just reloading the data from performance standpoint. I mean.
What do you recommend when we're trying to figure out the right publication strategy, and how do we go about it? We discuss try different strategies, and
I mean, you can try. No, I mean, there are usually there are certain certain patterns, certain queries, like typical queries that are executed in the system, things like that. Like typical, if you have like a typical like star schema, right? When you have certain big tables and then multiple reference tables, those reference tables are usually replicated, and then the rest of the tables they usually have something in common that you can collocate on, usually. But of course, that's case by case, So you need to analyze your data model that you have right now, and you need to make sure that the collocation is chosen in the way that it optimizes most of your queries. All right, we're out of time, actually. Thank you guys for coming. I hope you like the summit.